Hello everyone, my name is Siddhartha Reddy. Today I will be presenting an PathoVision and AI powered breast cancer detection system. This project is completed by the team Shreya, Susaina, Srivarshini, Karthik under the guidance of Dr. Suresh Kumar Mandala, Assistant Professor at School of CS and AI, SRU. Let me walk you through the problem, methodology, implement and results for this project. Breast cancer is one of the leading cause of the mortality among the women worldwide. Traditionally, histopathologist diagnosis is manual, time consumption, and often prone to human error due to subjective and the high volume of samples. PathoVision aims to assist pathologists by providing the faster, accurate, and consistent predictivity using deep learning. First, the introduction. Breast cancer is one of the leading causes of death among human. Checking tissue samples under a microscope takes a lot of time and causes time consumption, leads to mistakes. An AI pathologist can given by a best accurate and consistent results. Next, the problem statement. Manual image analysis is slower and depends upon the person doing it because there are so many images to examine, delays and misdiagnosis can happen. So, here is the need of an automated and reliable system that can help and classify the cancer images. Finally, the abstract. My project PathoVision uses two deep learning models like CNN and ResNet to classify breast tissue as benign or malignant. We used the IDC and BreakHis dataset and applied preprocessing and augmentation to improve the accuracy. We also added a Grad-CAM to show which parts of the images of the models focused on. All of this is provided through a sample web interface for the quick predictions. PathoVision uses a dual deep learning models approach. A custom CNN model trained on the IDC dataset, a resonance-based transfer learning model trained on the BreakHis dataset. We perform processing, image augmentation, and integrated CAM to provide an expandable predictions. Finally, the system is deployed through a sample and user-friendly web interfaces. Our proposed solution is to build an AM model that can classify the breast histopathology image automatically. We use two model architectures. A. CNN model for IDC binary classification. B. A resonance based model for breakage dataset. The system processes images predictivity and malignancy and generates a grade CAM heat maps for integrity responsibility. And we also provide a web interface for the real-time interface. A project includes the following steps are collecting and pre-processing datasets, that is IDC and break-ins, and applying pre-process and augmentation, building and training the CNN and resonant models, evaluating performance using accuracy, precision, recall and F1 score and AUC, integrated grade CAM for the visual explanation, building a web interface to display the predictions, deploymenting the final report. We use the two major datasets. First, the IDC dataset, which contains 27,542 images, patches of 50 cross 50 pixels. We used around 90,000 images for training due to n computational limits. The dataset is imbalanced, so augmented was necessary. Second, the break-hints dataset containing 9,109 high-resolution images across the multiple magnifications such as 40x, 100x, 200x, and 400x. The dataset is deal for learning fine-graded cancer subtypes. The system architecture follows a sample flow. The user uploads an histopathology image. The image is processed, resized, and normalized, and the appropriate model is selected. The model predicts whether the tissue is benign or malignant. A confident score is generated. Grade CAM produces a heat map showing important regions. The results are displayed through our web interface. Our methodology involves the four stages. Image processing, we perform the resizing, the normalization, augmentation and oversampling to handle the classes imbalance. CNN model for IDC. A custom CNN with three conventional blocks are is used for the binary classification. ResNet model for break-ins. We use ResNet 50 and DenseNet 201 with the frozen layers and custom classifiers leads to learn from high resolution images. Evaluation. We use confusion matrix, ROC curve, AUC scope, precision, recall, and F score. Grad-CAM helps visualize the regions influenced by the models and prediction. The technology stack includes Python, TensorFlow, Nasar, OpenCV, Flask, and backend. HTML, CSS, and JavaScript for the front end, and Grad-CAM for expandable AI. We also use Jupyter Notebook for the model development and training. The model achieved strong performance, particularly the resident model on BreakHis, which reaches an AUC score of 0.95. Both models demonstrated robust classification abilities across the varying magnifications. Grad-CAM is successfully highlighted the key cancerous regions being analyzed. This is the web interface we developed. The user can upload the histopathological images, receive an instant predictions, and also view the Grad-CAM heat map. The interface is designed to be simple, fast, user-friendly for the clients. PathoVision offers many advantages like fast and automated cancer diagnosis, reduces the workload for the pathologist, high accurate predictions using the state one of the art of deep learning models, a clean, innovative and web interface, and a scalable design for the real world client development. And our project timelines was structured into a dataset preparation, model deployment, evaluation, interface creation, testing, and final deployment phases. Each stage was successfully executed to ensure the high quality results. In the conclusion, the PathoVision demonstrated how an AI significant assist in early breast cancer detection. The system provides fast, accurate predictions and supports the client decision making with an expandable AI visualizations. Overall, the project shows that deep learning has strong potential to improve the healthcare outcomes. There are the academic references. These are the academic references that supports our methodology and model architectures. They include recent works in the breast cancer image classification, transfer learning, and transformers enables the models and multimodal approaches.
Hello everyone, in this video I'll quickly demonstrate my breast cancer classification web interface. This system analyzes histopathological images and classifies them into benign or malignant, and if a malignant it also predicts a subtype, if benign also it predicts a subtype. So this is the home screen of the web interface. Users can upload PNG, JPG or TF5 images. Let me upload an image. Once I have uploaded the image, the system confirms the upload, shows the file name and activates the analysis option. We have two models available, CNN and ResNet. I will select one and start the analysis. The processing screen shows all step processing, binary classification, subtype analysis, visualization. The process bar shows real-time updates. So for this image, the system detects as benign with a confidence score. Since it is benign, we also need to upload a subtype image. So let me upload a subtype image. So the system takes the input of the image and processes it and displays a subtype result, competence score, graph, and a short clinical explanation. So it displays that it is a tumor with 89% confidence and some classification matrices with along with clinical information. Here we can also view detailed visualization, export complete report, save results, and analyze new image. If we click on analyze new image, the data will be cleared and will be able to upload new image. And once we click on save results, this data will be saved into the database. So now let's just upload another image and see what kind of image it is. So now let's just check for another image. Now I will be uploading image and selecting the model, and so this image is malignant. The system detects it as a malignant. Now the interface asks for a subtype patch, that is, I'll be clicking a subtype patch. I'll upload malignant subtype image. The system process it and displays the subtype result, content score, graph, and a short clinical explanation. So this image is of a ductal carcinoma with 94% confidence and classification metrics, and with a clinical explanation. So the user can export the reports and store results in the database. Everything runs on a Flask backend, which loads the models, that is binary model.h5 and subtype model.h5, and processes images and returns prediction. All models are stored in models directory. Conclusion: this system provides quick, interactive, and accurate cancer analysis with subtype detection and visualization, and also stores the data in its database. So, this is a quick, interactive, and accurate cancer analysis system. Thank you for watching.